All right, hello and welcome back. We are in our Chapter 3 material, Thinking About Kinetics. In our previous video, we introduced collision theory, and we discussed how to measure and report our reaction rates. Now, in this video, we're going to introduce the idea of rate laws, how our reaction rates are affected by the concentration. We'll look at some ways to determine our rate laws, including initial rates approach and the integrated rates approach. All right, so rate laws tell us how our reaction rates are affected by the concentrations of our reactants and occasionally our products. If you have a balanced chemical equation, we can write the rate law for that equation according to this form. The rate is equal to some constant K times the concentration of each chemical species involved raised to some exponent. This constant we call the rate constant. These exponents we call the reaction order. More specifically, the exponent for each chemical is the reaction order with respect to that chemical, and the overall order of our reaction is the sum of all the exponents. What does this mean? Well, this rate law is an equation. It tells us, well, if we double the concentration of a specific chemical, does this make our reaction rate bigger? Does this make our reaction go faster? Or when we double our concentrations, does this make our reaction rate quadruple the speed? Or perhaps when we change our concentration, perhaps this does not affect the speed of our reaction at all. Right? Our rate law will tell us the relationship between concentrations and reaction rates. Moreover, the magnitude of this rate constant tells us if this is a very, very fast reaction or a very, very slow reaction. Right? This rate constant can have a wide range of magnitudes from very, very small to very, very large. Let's look at some simple cases. What if we have a balanced reaction, which is one starting material turning into some number of products? Our rate law, we can write this as the rate of our reaction is equal to a rate constant times the concentration of our reactant raised to some exponent. Here we're going to call it M. This M is our order, the order of the reaction, and there are a few values that are more common than others. Our reaction order is oftentimes 0 or 1 or 2. These are the most common things. Occasionally we have negative numbers and occasionally we have fractions, but these 0, 1, and 2 are the ones we will see most often. If we have a reaction order of 0, zeroth order reactions tell us that the rate of our reaction is equal to some constant times, well, a raised to the 0. Anything raised to the 0th power is just going to be a 1. In this situation, the reaction rate does not depend on the concentration at all. If we have M is equal to 1, we call this a first order reaction. That means the rate of our reaction is equal to K times the concentration of A. That means the rate is directly proportional to our concentration. Our rate will increase linearly with that concentration. Our last common option is if this exponent is 2. We call this a second order reaction. If we have a second order reaction, the rate is equal to K times the concentration squared. Our rate will increase exponentially with our concentration. If you triple the concentration, you will increase the rate by 9 times the speed. Our rate law here, it is an interesting statement, trying to figure out the relationship between the speed of the reaction and the relative concentrations. It is an equation that we have to determine experimentally. These rate laws, we can set up some experimental methods for determining what is the rate constant, what is the exponent related to each of our chemicals. We're going to introduce two ways of experimentally determining the rate law. The first way is known as the initial rates method, or the ratio of rates method. In this method, we are going to measure the reaction rate. Right? We talked about this in our previous video. We can measure reaction rates by measuring change in concentration over time. Maybe using spectroscopy, maybe by measuring mass, maybe by measuring polarizability of light. Any sort of method that we have of measuring the reaction rate will allow us to do this method. What we also need to know is the initial concentration for our reactions. If we can measure that reaction rate and the initial concentration, that will tell us, well, some of the unknowns in this equation. In order to solve our math problem, we need enough equations so that we have, well, the same number of equations as we have unknowns. Right? If we know the rates and we know the concentrations, we're going to need to do multiple trials in order to solve for the rate constant and all of these exponents. Let's go through an example to see what this looks like. Here's our practice problem. What is the rate constant for this reaction? What is the rate law for this reaction? Well, okay, we have a balanced chemical equation. Two of these NOCLs form two NOs and a Cl2. The rate law for this balanced reaction is written in the form the rate is equal to our rate constant times our concentration of our reactant raised to the exponent m. Notably here, we have a coefficient in our balanced reaction. That does not matter. That does not tell us what our exponent is. That does not tell us what our rate constant is. The balanced reaction here actually only tells us what to include in terms of which chemicals. Typically, our rate law only includes our starting materials raised to some exponents. All right, with our balanced reaction, we can write out our rate law. Rate is equal to K times concentration raised to the M. Now we need to do some experimental data. Here we've run 3 trials. With a concentration of 0.1 molar NOCl, the initial rate is 8 times 10 to the negative 10. When we double that concentration to 0.2 molar, our initial rate has increased to 3.2 times 10 to the negative 9th molar per hour. And lastly, when we go up to 0.3 molar as our initial concentration, our initial rate is 7.2 times 10 to the negative 9 molar per hour. All right, this is our problem. Let's set up our answer by plugging in all of these values into our rate law equation. So the rate is equal to K times our concentration raised to the M. Well, let's write that out for each of these trials. For trial 1, our rate is 8 times 10 to the negative 10. This is equal to K times our concentration, which is 0.1, raised to the M. For trial 2, we can do the same thing. We have 3.2 times 10 to the negative 9 is equal to our rate constant times 0.2 raised to the M. And likewise, we can do this with our third trial, 0.3 and 7.2 times 10 to the negative 9. Now we have 2 equations, and in these 2 equations, we have 2 unknowns. This is a set of equations that can be solved. We're trying to solve for K, we're trying to solve for M. Well, if we have 2 equations, we can divide them by each other and have also a true statement. So let's divide this first rate law expression by that second rate law expression. And what we end up with is, well, 8 times 10 to the negative 10 divided by 3.2 times 10 to the negative 9. That is what we get on the left side of our equation. On the right side of the equation, we have k divided by k, and we have 0.1 to the m divided by 0.2 to the m. Nicely here, our k's will cancel out. K divided by k is just 1. And in addition, we can simplify this statement on the right. We can say that 0.1 to the m divided by 0.2 to the m is going to be 0.1 over 0.2 quantity to the m. On the left side of the equation, we just have some number. On the right side of the equation, we have a fraction raised to the mth power. In fact, we have 1/2 raised to the mth power. This is something we can solve. If you want to be rigorous about this, and why not, let's do it, we can take the log of each side. If we take the log or the natural log of the left side of this equation, we can take the natural log of the right side of the equation, we're going to get some number. On the right side of the equation, well, we can use some log rules and say that this is going to be equal to m times the natural log of 0.1 over 0.2. All right, one last little bit of algebra here. We can solve for m, divide across so that we only have m on one side of the equation, plug it all into the calculator, we can get our answer. M is equal to 2. And this is what we expect. We expect one of our most common answers, either 0 or 1 or 2. In this case, our answer is very, very close or exactly 2. With experimental data, maybe our numbers are not exactly 0, 1, or 2, but oftentimes it's close enough where we can round to those nearest whole numbers. Let's summarize here. When we're doing our initial rates method, we want to write out our rate law. In this case, our rate law is, well, the rate constant times our only reactant raised to some exponent. We're going to perform some experiments where we know the concentrations and we can measure the initial rates. For each of our trials, we can write out that rate law expression with the numbers filled in. Once we have enough trials, we can try to solve a system of equation, divide one of these rate laws by another so that we can solve for one of these exponents. The algebra from there is a little bit of some practice with using exponents, using logs, trying to solve this system of equations. But this is something that we can do. We have another practice problem here. This one's a little bit more complicated. Now we have two reactants combining together to form some products. We'll do the same strategy. We can write out our rate law expression. The rate is equal to the rate constant times our concentrations raised to some exponents. The exponent for each chemical is going to be unique. And we can perform some experiments. Now we know the initial concentrations for two of our chemicals, and we measure the initial rate for the overall reaction. If we can plug in these numbers to this equation, we can write out, well, 4 different equations and try to solve. Right? Try to write out our system of equations, divide one by another. In this case, since we have 3 unknowns, we want to choose carefully. If we choose carefully, we can get all but a single variable canceling out when we're doing this. Please do try your hand at this, and we will go through this problem and similar problems together in class. All right, we have a second method for determining what our order of our reaction is, determining what our rate constant is, and ultimately figuring out exactly what our rate law is for a given reaction. Our second method is known as the integrated rate laws method. Here we're using a little bit of calculus and trying to figure out some characteristic relationships between our concentration across various time points. Let's look at this one at a time. If we start with our simplest case, if we have m is equal to 0, we call this our zeroth order reaction. Our rate law is going to be k times 1. Our rate law is just a constant, k. The rate is equal to k. Here we have this written out. Rate is equal to k. Well, we can write out what our rate is. Our rate, like we saw in previous videos, is going to be related to how our concentration of reactants is changing over time, with this negative sign because our reactant is disappearing. This is our rate law expression, new this video. This is our rate expression, which we learned in our previous video. Well, we can tie them together. Negative change in concentration over change in time is equal to k. We can do some calculus. If you want to, take the integral of this whole expression. Our class is not calculus based, and that's okay. We can jump right to the answer. It's not too hard of an integration if you want to try it yourself. But the result here is we have a relationship between the concentration of our reactants over time. What we find, the concentration at any point in time is equal to negative k times t plus our concentration at time point 0. A sub 0, this is our initial concentration. This expression looks like the equation for a straight line with a negative slope of k. Let's look at this graph, right? If we plot the concentration versus time, we can see for zeroth order reactions, the concentration will decrease linearly based exactly on our rate constant k. The slope of this line is exactly negative k. What does this tell us? Well, if we can measure the concentration over time, we can try to create a graph like this. If we see a linear relationship between concentration and time, this tells us that our reaction is exactly zeroth order. Right? We can work backwards here. If we're measuring concentration over time, maybe with spectroscopy, maybe using pressures, maybe using mass, whatever we can do, if we can measure the change in concentration over time, well, if we find that relationship is linear, that tells us our reaction is zeroth order. And if we make this graph, we can solve for the slope, and that will tell us exactly our rate constant. Fantastic. What if we don't have a zeroth order reaction? Right, we said there are actually 3 common orders for our reaction. Well, we can think about the same type of approach for first order reactions. For our first order reactions, this exponent is equal to 1. And so we see that our rate is equal to k times the concentration. As we saw before, the rate can also be expressed in terms of the change in concentration over time for our reactant disappearing, right? Include that negative sign. And now we can tie these two equations together. With a little bit of rearranging and a little bit of calculus, now we can solve for, well, how does our concentration vary with time for first order reactions? The result is a little bit different. Now we can see that the natural log of our concentration is equal to negative kT plus the natural log of our concentration at time 0. This, once again, looks like a linear relationship, but now our relationship is only linear when we're looking at the natural log of concentration versus time. So, okay, once again, we can try to measure how our concentration changes at various points in time and make this second graph where we have the y-axis as the natural log of our concentration. If we make this graph and we have a directly linear relationship between natural log of concentration versus time, that tells us that our reaction has to be first order. Once again, the slope of this line is related exactly to the rate constant for our reaction. Negative k is equal to the slope. If we find this graph is linear, we can determine what the slope is, which will dictate what our rate constant is. Notably, if we have a first order reaction, this graph will be linear, but the graph of concentration versus time that we saw on the previous slide will not be linear. Only one of these can be linear at a time. The other one will be more like a parabola. So, okay, if we want to determine if a reaction is zeroth order or first order, we can make two graphs. Whichever one is most linear will tell us the order of the reaction. All right, hold on. We did say there was a third option. Well, we can do the same kind of approach. We end up needing to make three graphs to determine which is most linear, to determine what is the order of our reaction, but we can certainly do that. Let's look at our second order reactions. We have the rate is equal to k times the concentration squared. We have our same expression for the rate of our reaction. We can tie these two things together, do a little bit of calculus, and come up with a new expression. In this expression, we have once again a linear relationship, but now it's between the inverse concentration and time. We can say 1 over the concentration, or the inverse concentration, is equal to positive kT plus 1 over the concentration at time 0. Right, so here we can make this third graph. If we plot 1 over the concentration at various points in time, sometimes this third graph will be linear, and if it is, that means we have a second order reaction. All right, now we have all the tools. We can summarize this in our slide here. If we want to determine the order of our reaction, here's our integrated rate method. We can make three different graphs: the concentration versus time, natural log of concentration versus time, 1 over the concentration versus time. Only one of these graphs will be linear. Whichever one is linear will tell you which order your reaction is. If they're not linear, they might look like slightly curved lines or parabola lines. Right? Only one of these will be exactly linear. Once we know what the order of our reaction is, we can use the slope of those graphs to figure out what our rate constant is. And there we go. We've determined everything we want to from our rate law. We can see this in our practice problem. Here we have hydrogen peroxide decomposing into water and oxygen. We've monitored the amount of hydrogen peroxide that there is over various points in time, and we can see what that looks like here, right? Concentration of hydrogen peroxide over 15 hours. Concentration decreases over time. Is this graph linear? Well, does not look exactly linear. Our best fit line, this dotted one here, does not touch all the points on our graph. Let's check our other graphs. We can also make a graph with the natural log of concentration over time. This graph looks much more linear, right? We can see that our dotted line basically is right on top of every single data point that we have. Just to be safe, we can make a third graph. We can plot 1 over the concentration versus time. And we can see, okay, this does increase, but this increase is not linear, right? Our best fit line, this dotted line, does not touch all of our data points. So which graph is most linear? It's going to be this natural log plot versus time, which will tell us that, okay, our reaction has to be exactly first order. If we have a first order reaction, well, we can use Excel or whatever graphing program we have to give us a best fit line. We know that our reaction is first order. We can also determine the rate constant. Our rate constant is going to be related to the slope of our line. K has to be equal to, well, it's always a positive number. The rate constant is always positive. But we can just take that value, right? K is equal to 0.116. And there we go. For our rate law, now we can write the rate is equal to our rate constant, 0.116, times concentration of hydrogen peroxide raised to our exponent, which is, well, just 1. The 1 we don't even need to write. There we go. Here is our complete rate law. Our rate law and this integrated rate law equation is also really useful. We can use this to determine the concentration at any point in time. Our question here is, okay, at time is equal to 20 hours, what is going to be our concentration? Well, our equation says that the natural log of our concentration is equal to negative KT plus the natural log of our initial concentration, which, okay, in this case, it's just 0. But now we know, well, the equation, we can plug in whatever value we want for that time. Careful here, when we plug in T is equal to 20, we want to solve not for the natural log of concentration, we want to find just the concentration. And so we can undo that natural log by using our exponential function. E raised to the left side of the equation will allow the natural log and this E to cancel out. E raised to the right side of the equation, okay, that can give us just some number, 0.098 molar. All right, one additional thing we can consider when we're looking at our reactions. We can think about our reaction half-life. The half-life of our reaction is how long it takes for 1/2 of our initial concentration to be consumed. Right? How much time does it take to use up half of our starting materials? Or to put this as an equation, the time when our concentration is 1/2 of our initial concentration. We can take this expression and use our integrated rate law equations to find, well, what we expect our half-life to be for any order of our reactions. The most interesting is when we have first order reactions. For first order reactions, we have this natural log equation. The natural log of A is equal to negative KT plus the natural log of A naught. Well, if you replace our concentration of A with 1/2 A naught, we get this new expression. And solving for the time here, solving for the half-life, actually, interestingly, allows the concentration, or the initial concentration, to drop out of the equation. What we find is the T1/2, the half-life for for first order reactions anyways, is equal to 0.693 divided by the rate constant, or the natural log of 2 divided by the rate constant. The half-life for first order reactions does not depend on how much of your material that you start with. That's fascinating. That's interesting. That means our first order reactions at any point in time, well, after one half-life, you'll lose half of that. After the same amount of time, you'll lose another half, right? You'll drop from 100% to 50% in one half-life. After the next half-life, you'll drop down to 25% and then down to 12.5%. But this happens at a steady interval. Our half-life is constant for these first order reactions. Delightful. We can do a similar approach for our zeroth order and second order reactions. The answers end up being not quite as delightful because they do depend on our initial concentrations. For zeroth order reactions, we end up with this expression. For second order reactions, we end up with this expression. Okay, let's wrap this up. Let's go back to our practice problem here. One last piece of it. We have that same reaction. We have the same graph. We want to decide what is the half-life for our reaction. Well, we said this was our first order reaction. And therefore, the half-life is equal to the ln of 2 divided by our rate constant k. The natural log of 2 is just a number. Our rate constant, remember we determined this earlier, 0.116. Great. Our half-life here, 5.97 hours. That means every approximately 6 hours, you'll use up exactly half of however much hydrogen peroxide you have, right? If we started with 1 molar of our hydrogen peroxide at our initial time point, well, in 6 hours, we'll be down to half a molar. In 12 hours, we'll be down to, well, a quarter molar, and so on and so forth. In fact, we can zip back to the beginning of this practice problem and visualize this, right? Here's the concentration over time. In about 6 hours, we'll drop down to 0.5 molar. We're starting here at 1 molar. How long does it take to get to half of that? This is about 6 hours. In order to get down to half of that, this is going to take, well, another 6 hours. If you were trying to get down to half of that, it will take the same interval of time. This will happen around 18 hours, right? And so on and so forth. For first order reactions, we have a constant half-life. Your concentration will be cut in half at a steady rate. All right, I hope this has been interesting. We've introduced our idea of rate laws and a couple of methods for how to experimentally measure those rate laws. Please let me know if you have any questions. I look forward to seeing you in the next video. And as always, I hope you have a great day. Thanks.